Hello, everyone, and welcome to this explainer. Before a massive suspension bridge ever bears the weight of a single car, or a new airplane takes its very first flight, they've actually already survived thousands of lifetimes, but virtually. Today, we're exploring a completely monumental shift in engineering and design, because let's be real, we've officially moved way past the old days of physical trial and error. We've entered this amazing era where digital tools give engineers what is, quite literally, a superpower. We're going to be looking at how one specific platform, ABAQUS, serves as the ultimate bridge between your standard computer-aided design and actual, real-world virtual performance.
Okay, let's dive into this with a really high-stakes scenario to get us started. How exactly do modern automotive manufacturers manage to crash test thousands of cars without ever bending a single piece of real metal? I mean, it sounds a bit like magic, right? But it's purely the power of simulation. Just think about it for a second. A single physical crash test prototype can easily cost upwards of $500,000. So crashing 1,000 of them just to, say, perfect a crumple zone, yeah, that is completely financially impossible. There's no way. And that is exactly where the magic of virtual testing takes over. It acts as this incredible secret engine that's powering modern innovation and really keeping development moving at absolute warp speed.
So, traditionally, engineering was kind of trapped in this costly, really relentless loop of physical trial and error. The old way basically went like this. You build a physical prototype, you break it on purpose, you take a highly educated guess as to exactly why it broke, and then you start the incredibly expensive process all over again. Today, digital engineering completely flips that script. We can now evaluate intricate designs and push them to their absolute breaking point virtually, long before a single manufacturing machine is even powered on. It accelerates the entire development timeline, it drastically cuts down on overhead, and, this is huge, it totally eliminates massive amounts of physical waste that used to just end up sitting in a scrap heap. Now, you might be wondering, why this sudden urgency behind this massive digital shift? Well, it ultimately comes down to one word: complexity. Whether an engineer is designing an intricate aircraft wing, a massive suspension bridge, or even a microscopic medical stent, the requirements they're facing right now are incredibly strict. Modern products don't just get to work in a vacuum, right? They absolutely must guarantee safety under really extreme conditions. They have to ensure long-term durability over decades, operate with absolute peak efficiency, and hit these rigorous global sustainability targets. Trying to hit all of those marks perfectly using just physical prototyping, it's simply not viable anymore. It's an impossible investment of both time and resources. So the actual computational engine making this massive virtual leap possible is called finite element analysis, or FEA for short. Essentially, what FEA does is it takes a massively complex structure and mathematically breaks it down into thousands, and honestly, sometimes millions of tiny, manageable geometric pieces or elements. From there, it simulates exactly how each individual little element responds to extreme, real-world conditions. We are talking about crushing physical pressure, wild temperature shifts, intense mechanical vibrations, you name it, even massive blunt force impacts. By mathematically calculating all these responses at such a granular level, engineers can identify potential catastrophic issues incredibly early in the process. It's all about neutralizing those project risks way before they ever get the chance to manifest in the physical world. And this brilliantly illustrates the core difference we're talking about here. Think of traditional CAD, computer-aided design, like a highly detailed, brilliantly constructed digital photograph. I mean, it gives you perfect geometry, sure, but at the end of the day, it's completely static. ABAQUS, on the other hand, is the high-definition action movie. It takes that pristine, static model and just ruthlessly subjects it to brutal operational loads and completely chaotic real-world environmental conditions. It wants to see exactly how the design behaves when things get rough. Basically, it animates that static geometry with real-world physics. Let's move to and see how this builds into an actual workflow. How do we actually get from that static photograph to the dynamic action movie? Well, it's a really elegant, seamlessly integrated three-step process. First off, engineers import their highly detailed CAD model directly into the simulation environment. Next, they define the precise material properties. So maybe it's an aerospace-grade carbon fiber or perhaps a high-tensile steel. And then they set the loading conditions, mimicking the exact weight, heat, or friction it's going to face out there in the real world. Finally, the software just takes over. It churns through these incredibly complex physics algorithms to calculate and predict the product's true physical behavior. That streamlined, almost effortless transition is exactly what keeps modern product development cycles moving so incredibly fast today. And once those heavy calculations finally finish processing, wow, the sheer volume of data-driven insight that comes back is just staggering.
Engineers aren't just getting a simple pass or fail grade here. They receive these highly detailed, color-coded maps of stress distribution, highlighting exactly where a specific component is feeling the absolute most pressure. They can vividly see deformation patterns, which reveals exactly how a material is going to warp or buckle under a heavy load. But most importantly, they can pinpoint exact potential failure points. This completely transforms static designs into incredibly robust, dynamic engineering solutions. It literally replaces all that old physical guesswork with hard, actionable data. Actually, to quote the source material directly here, virtual testing enables organizations to identify design weaknesses before production begins. Honestly, that is essentially the holy grail of modern manufacturing. Just think about the massive ripple effect that has on a business. Catching a critical structural flaw on a computer monitor instead of out there on a factory floor, that saves millions of dollars in wasted materials. It prevents those catastrophic, multi-month development delays, and it goes beyond just fixing errors, too. Simulation-driven optimization allows engineers to confidently shave off excess material. That makes their products lighter, stronger, and significantly more efficient, all while maintaining absolute 100% safety. It's a total game changer. Because this software is just so exceptionally robust and versatile, it essentially acts as the digital backbone for almost every high-stakes industry you can possibly imagine. In aerospace, they use it to evaluate long-term fatigue on airplane wings and to test out next-generation composite materials. Over in the automotive sector, it's heavily relied upon to ensure crashworthiness and everyday durability on the road. Civil engineers use it to model the structural integrity of bridges, massive hydroelectric dams, and they even use it to simulate how high-rise skyscrapers will flex and react during a catastrophic seismic event. The sheer scope of complex, real-world problems that this technology solves is absolutely fascinating. I actually want to pause for a quick moment specifically on the biomedical applications, because this is where the direct human impact becomes so incredibly profound. We aren't just talking about buildings and planes anymore. Engineers use this exact technology to simulate the highly complex interactions between soft, living biological tissues and engineered medical devices. Think of something like a titanium hip implant interfacing directly with natural human bone. By virtually engineering these exact interactions right down to the microscopic level, researchers can totally fine-tune a device so that it works in perfect harmony with the human body. This directly improves patient comfort, functionality, and long-term health outcomes. Virtual engineering is literally changing lives here. So, with all that being said, where is all of this incredible technology heading next? Well, the future of engineering is undoubtedly digital, and simulation sits right there at the very center of it all. We are entering a landscape that's increasingly dominated by digital twins. If you haven't heard of them, they are basically these constantly updating, living virtual models of real-world physical assets. We're also seeing the rapid integration of artificial intelligence to optimize these designs in real time, and it's all powered by the massive decentralized scale of cloud computing. As we move forward into Industry 4.0, simulation data won't just be used to design a product, it will actually be used to intelligently predict exactly when a product needs maintenance years and years after it's actually been built. Which really brings us to a final, compelling thought I want to leave you with today. How will simulation-driven design shape the safety and efficiency of the next product you rely on? Because whether it's the smart car you drive tomorrow, the suspension bridge you commute over, or even a life-saving medical device, predicting real-world performance virtually is no longer just a luxury or some neat little competitive advantage. It is the absolute foundational requirement for modern engineering excellence. Thank you so much for joining me for this explainer today. I really hope it sparked your curiosity, and I definitely encourage you to keep questioning exactly how the designed world around you actually comes to life.